Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 20, Organic Chemistry 1. Today we will start on chapter 6, Stereochemistry. Isomers are compounds with the same molecular formula but different in molecular arrangement. We can classify the type of isomerism, two different types, structural isomerism and stereoisomerism. In structural isomerism, we have a chain, positional, functional, metamerism, tautomerism, and ring chain. In stereoisomers, we have geometrical isomers and optical isomers. Structural isomerism. In structural isomerism, the atoms are arranged in completely different order. Chain isomerism is an example. This isomer arises because the possibility of branching in the carbon chain. We have here pentane 5 carbons in one sequence. 1, 2, 3, 4, 5. Isobentane has the same molecular formula C5H12, but we have carbon 2, 3, 4 carbon in a chain and one branch methyl. That's completely different compound. Here we have chain of 3 carbon, 1, 2, 3, and 2 methyl branch. That's new pentane. Again, different compounds. Positional isomerism. The basic carbon skeleton remain unchanged, but the important groups branch are moved around on that skeleton. So we have 1, 2, 3, 4 carbon chain. We have butane, but the bromine here is carbon 1, so it's 1 bromo. It's completely different from 2 bromo compound where the Br is located on carbon number 2. Functional group isomerism. The isomers contain different functional groups. That is, they belong to different families of compounds. Here we have 1, 2, 3, 4, 5 carbon, C5H10O, but the function group here is aldehyde. We have pentanal. Here, again, we have 5 carbon, pentane, 2 on. We have ketone functionality. Here, bent 4 in 1 ol. We have in ol functionality. We have alkene and we have an alcoholic functionality with the same molecular formula C5H10. We call this functional group isomerism. Metamerism. They have compounds having the same molecular formula but different number of carbon atoms on either side of the functional group. Like here, the functional group is ether. This side we have ether group, we have this inside ether group. Again, the same ether functional group, but we have here 1 methyl and here is 1 other propyl group. Okay, so number of carbons in both sides, the sum of them is 4. 1, 2, 3, 4. 1 and 3 is 4. So the same molecular formula, but again, it has different number of carbon atoms on either side of the function group. The function group here is ketone. Once again, we have here propyl and here methyl. On this side we have an ethyl, so same molecular formula, same function group, but again the number of carbon on each side of the function group are different. Tautomerism. Tautomerism is a phenomenon where a single chemical compound tend to exist in two or more interconvertible structures that are different in terms of the relative position of one atomic nucleus, which is generally the hydrogen. Here we have keto functionality, keto form, and if the oxygen is going to take this hydrogen, and these two electrons will move to form double bond, and the carbon oxygen bond will move to oxygen, that will lead to enol in double bond all OH. So it's better to draw the structure, the arrow this way, so we have just only one and two. Ring chain tautomerism. When the movement of the proton is accompanied by the opening or closing of ring, it's called ring chain tautomerism. See, we have here ring, and we have here chain. They are interconvert to each other, and we call that ring chain tautomerism. This type of tautomerism is well observed in carbohydrate. As a model, D-ribose is carbohydrate molecule with 5 carbon. This oxygen has 2 electrons on the oxygen, so it is nucleophilic site. That nucleophilic attack, kicking the pi electrons of the carbon oxygen bond toward oxygen, followed by H transfer as a second step to form the ring, and this is a chain, so we call that ring chain tautomerism. In stereoisomerism, molecules have the same molecular formula and the same sequence of bonded atoms, but differ in the three-dimensional orientation of their atoms in space. These isomers we call geometric isomerism. This isomer occur when you have restricted rotation somewhere in the molecule, like you have carbon double bond carbon, or if you have a ring. So you have restricted rotation. Two different groups on left hand end of the bond, double bond, and two different groups on the right hand end of the bond. It doesn't matter if they are the same or not, same group or not. Cis-Trans terminology. In order to use the Cis-Trans terminology to differentiate stereoisomers, there must be two identical groups to compare. The cis-stereoisomer exhibit groups on the same side of the ring or double bond, while the trans isomer exhibits groups on the opposite sides of the ring or on the double bond. The term cis and trans are also used to describe stereoisomerism among the double bond. So we have ring, we have two methyl groups on the same side. That's why we call it cis. If we have these two methyl groups on the opposite sides, we call that trans. We have the double bond here. If we have the two methyl group on the same side, cis, on the opposite side, they are trans. Chlor and chlor on the same side, so it's cis. Here, we have the double bond in here. We have two identical groups on these two carbons. So, these two are trans to each other. So, this compound will name 1, 2, 3, 4, 5, 6. So, on the carbon 3, we have methyl, so 3 methyl, hex, 3 in, and of course trans. Here we have methyl and chlor on the other side. Where is the two identical to compare with? Oh, you have here hydrogen, you have here hydrogen. So we are going to compare with these two hydrogen. They are on the opposite side. So this compound we'll call trans 1-chloro-prop-1-ene. Now, here, these two carbons, they don't have two different. Here is H, where the different groups, there are not different groups. When two identical groups are connected, like the chlorine on one carbon, there cannot be cis and trans isomerism, and we call the compound without terminology cis or trans, we call it 1,1-dichloro-prop-1-ene. Chirality. A molecule is chiral if it is not superimposable on its mirror image. Most chiral molecules can be identified by their lack of plane of symmetry. There is no plane of symmetry in the molecule, so we call this chiral molecule, or they don't have any center of symmetry. In this molecule, we have a mirror compound, mirror to it, which is not superimposable to it. This is one, and this is the mirror. They are not superimposable, as you can see. Chlorine over chlorine, bromine over bromine. Now, if you have here methyl, it's over hydrogen, and hydrogen over the methyl. So it's not superimposable. لا يمكن ينطبقوا تمام الانطباق على بعض. That's why I call this molecule chiral molecule. Okay? This is using models. You can see that this over this and this over this, but then hydrogen with methyl and hydrogen with methyl, they are not superimposable. Now this molecule, when you have carbon carrying two identical group, okay, this is a mirror compound, but if you turn this 120 degree, rotate it 120 degree, they will be superimposable. Okay, and you can see in that molecules a plane of symmetry. So if you have a plane of symmetry, you have a chiral molecule. You have a chiral molecule, which means that this molecule with its mirror image will be superimposable. This molecule has a plane of symmetry. That's why this molecule has a plane of symmetry through the center carbon. This is a mirror plane. In other words, one half of the molecule is perfect reflection of the other half of the molecule. This molecule is not chiral, of its mirror plane. We call it a chiral molecule. This is a chiral molecule. This molecule has bromine to bromine, hydrogen to hydrogen, chlorine to chlorine, via what we call it center of inversion. It's another symmetry element, I. This molecule has a center of symmetry, I, or an inversion center, and it is not chiral, a chiral compound. This is a chiral compound. This molecule, 1,2-dichloro cis 1,2-dichlorocyclopentane, has a plane of symmetry. This molecule is not chiral because of its mirror plane, a chiral molecule. But if we look for a trans, the trans has no plane of symmetry. This molecule has no plane of symmetry, and it is chiral molecule. In alene compounds, when you have carbon, double bond carbon, double bond carbon, you have this carbon sp hybridize, and these two double bonds are not on the same plane. They are perpendicular to one another. Okay? See, these two hydrogens are in one plane, and this hydrogen will be in the back, and this in front of the plane. Okay? So there is a plane of symmetry, and this molecule is a chiral molecule. If we have monosubstituted, again, you have this Br and this hydrogen will be divided by the plane into two equal pieces, and these two hydrogen will be mirror image to one another. So there is a plane of symmetry, and this molecule is a chiral molecule. See in here, this monosubstituted, okay, and they are mirror image to one another. This is a mirror to that, okay. If you really get them together, they are superimposable. So they are identical. This molecule is a chiral molecule. In this dibromo alene compound, the Br and hydrogen atoms will be divided by the plane, okay, but the hydrogen is not mirror image to the bromine, so there is no plane of symmetry, and this molecule is chiral molecule. This is a brom, and this is a brom, dibromo, mirror. This is a mirror, okay. If you get them together, so this bromine will be with hydrogen and this hydrogen will be with bromine. These two are not superimposable, and this molecule is a chiral molecule. And the line between carbon, 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 we call it chirality X. On the other hand, if you have the dibromine, the two bromine on one carbon, then you have a plane of symmetry, and this molecule is a chiral molecule. In the diphenyl, when you have diphenyl compound with also substituent blocking the carbon rotation with no plane of symmetry, then you have chiral molecule. These two mirror image are not superimposable. Get them together, you will find nitro with nitro, COH with COH, but then COH with NO2 and NO2 with COH, so they are not superimposable. And this is a chiral molecule that is isomerism. Asymmetric carbon atom, what we call it chirality center and stereocenter. Asymmetric carbon atom or chiral atom is a carbon atom that is bonded to 4 different groups designated by star, asterisk. An asymmetric carbon atom is the most common example of chirality center. In IUPAC term, for any atom holding a set of ligand in a spatial arrangement that is not superimposable to its mirror image, we call it asymmetric carbon. Chirality center. Chiral center. Chirality center belong to an even broader group called stereocenter. Stereocenter or stereogenic atom is any atom at which the interchange of two groups gives stereoisomers. Chirality center means that you have 4 different groups on the atom, right? So this carbon, we call it chirality center. This nitrogen, we call it chirality center. The carbon on the first, this one, we can also name it stereocenter. The nitrogen, we can call it stereocenter. Here, this carbon, we can call it stereocenter. And this carbon too, we can call it stereocenter. Why? If you change this group with the hydrogen, replace them, you get completely different compound. We get stereoisomer of that compound. That's why we call it stereocenter. In trialkylamine, where you have lone pair R1, R2, R3, these molecules, we cannot consider it as a chiral. Even again, you have center, nitrogen center, with 4 different groups, including lone pair. Why? Because of the rapid inversion occurs between these 2 enantiomers. That's why it is a chiral. If you transfer the trialkylamine to quaternary ammonium salt with 4 different groups, then you get chiral molecules. You can get chiral molecules. If you have the phosphate ester The phosphorus center of organic phosphate ester is tetrahedral and thus is potentially stereocenter. This phosphorus potential stereocenter. Identify all chirality center in each of the following compounds. Vitamin C, here is a chiral center, another chiral center. Chiral center means that atom carries 4 different groups. So this carbon carries H, carries OH, carries CH2OH, and carries the whole group. So this carbon carries 4 different groups. Okay, here hydrogen, and then so hydrogen is 1, 2, 3, 4. So they are 4 different groups. Captopril, this is a chiral center. Again, you have here hydrogen, COOH, N, and you have carbon, you have here nitrogen. So this carbon is chiral center. What else? This carbon, H, CH3, CH2SH, and C double bond O. So this carbon carries 4 different groups. The third molecule has one single chiral center. This is not chiral center because you have 2 identical groups, phenyl and phenyl. Okay, again, this one is not chiral because this is methyl and this is methyl. To be chiral center, it has to carry 4 different groups. The 3-dimensional representations of the following compounds below, which have asymmetric carbon atoms, which have no asymmetric carbons but are chirals anyway. For the first compound, we can check this is asymmetric carbon. It has methyl, it has CH2, it has C double bond C, it has CH2, CH2, 4 different groups, so it is asymmetric. This carbon has 2 hydrogen, so it is not asymmetric. Again, this is not asymmetric, this is not asymmetric. This one has CH2, it has H, it has here CH2, CH2, it has CH double bond. This is asymmetric, so 2 asymmetric carbons and no plane of symmetry, so this molecule is chiral molecule. This carbon, asymmetric carbon, this carbon is asymmetric carbon. In MB, we don't have no asymmetric carbons, but the molecule is chiral due to the restriction of rotation around CC1 prime, 1 prime. There is no rotation around this carbon carbon bond. So this molecule and its mirror image compound will not be superimposable. That's why this is a chiral molecule. In this molecule, the also substituents are small. Okay? So we are expecting rotation around this carbon bond C1 prime, and this molecule can be at any time planar molecule and has a plane of symmetry, no asymmetric carbon, and the groups are not large enough to restrict rotation around C1 prime. The molecule has a plane of symmetry and it is a chiral molecule. See you in the coming lecture.